Hello, everyone. Good morning and good evening to all of you for joining us from various parts of the world. A very warm welcome to you all. I am Samuel, part of Hinduja Tech team, moderator for this webinar as well. I'm excited to have you all for today's webinar on demystifying digital twin and AI. This is going to be an interesting session where you're going to witness some innovative approaches towards product reliability. This webinar is brought to you by SMS Think Tank and Hinduja Tech. Before introductions, I want to set some ground rules. This is a live webinar planned for 59 minutes, presentation for 45 minutes, and Q&A for 14 minutes in the last. You may feel free to drop in your questions and in the comment section of the LinkedIn Live window at any given time. We will answer as many questions as possible during the Q&A session. In case your question is left, not to worry, we will ensure that we'll get back to you through our fulfillment package after the webinar. I request you to send your contact details from your work email ID to marketing@hindujatech.com as displayed on the screen. Once again, thank you for joining us. Wait till the end to make best use of the session. I'm sure you'll have an awesome next 45 minutes. I'm handing over the session to our panelist, Ed Lazinski, CEO and co-founder of SMS Think Tank. Over to you, Ed.
Thank you, Samuel. Hello, all. My name is Edward Ledzinski, and I'm the CEO and co-founder of the SMS Think Tank. In 1978, I joined IBM as a research and development engineer. And during my career with IBM, which lasted over 30 years, I've worked in many different positions within engineering, including systems engineering, systems research, systems product design and development, and various analysis and simulation projects. I serve on the NAFEMS America Steering Committee and have served on that committee for over 20 years. And I'm the co-founder of the Stochastics Working Group, Simulation Data Management Working Group, and the Joint and COSI NAFEMS System Modeling and Simulation Working Group. I'm an engineering graduate of RIT, that's Rochester Institute of Technology, and performed my graduate work in engineering and business at RIT and UNCC, University of North Carolina, Charlotte, respectively. Over to you, Vijay.
Thanks, Ed, for that introduction. Hello, all. My name is Vijay. I lead digital consulting and solutions practice at Hinduja Tech. I work with global automotive organizations, enabling them to take better decisions using data. In this webinar, I look forward to share one of our experiences in AI model development that solved specific business problems in engineering and service domains. In my professional capacities, I have worked with global manufacturing organizations in the past in the areas of digital transformation consulting, AI services, and software products management. I hold graduate degree in mechanical engineering and postgraduate degree in business administration from IIM Calcutta. Welcome to this webinar, and I hand over it to Frank for his introductions. Over to you, Frank.
Yeah, thank you very much. My name is Frank Popielas. I'm the managing partner and co-founder of SMS Think Tank. I have over 20 years of experience in the automotive industry globally, working for Dana in the area of engineering and research and development. I've worked in many different positions within engineering, including product and materials development, CAE testing, systems engineering. My main focus was on establishing a sound foundation and governance for simulation and systems engineering. Similar to Ed, I serve on the NAFEMS America Steering Committee, and I'm a co-founder of the Joint and COSI NAFEMS Systems Modeling and Simulation Working Group. I received my master's degree in engineering, majoring in theoretical physics from the Technological University in Moscow, Russia. I have over 35 granted patents in the areas of sealing, shielding, and fuel cell, with the focus on the automotive industry, and well over 40 global publications. With that, I would like to start the webinar content itself. During our webinar, we will cover first, of course, where we are today, setting the stage with market challenges, etc., going into the details of the digital twin and AI, then talking about a practical case study in product reliability before we are wrapping up our today's webinar. Let's start with setting the stage. As mentioned, I will talk about market challenge and associated engineering trends, talk about business drivers for the automotive industry, and key pain points in the automotive industry. First, let's set the stage with looking at some of the major market challenges. Global economy. We are more interconnected than ever, even if we don't see it directly. Faster than ever changing, evolving technology. The pace of technology development and corresponding model changeovers has dramatically increased and is in certain industry an almost ongoing phenomena. The age of data and information. We rely for most of our activities on data, but not only do we want to have access to the data, but we also want to make use of it, connect it so it can become information. Digitalization, visualization, collaboration. In our virtual-driven age, we need to ensure data information is easily digitally available and processable. It can be looked at and understood in an easy manner, and we are able to get in contact with each other seamlessly throughout all levels of our life, might it be professional or personally. Complexity. What was mentioned before makes everything, might it be a product or service, much more complex. This challenge needs to be addressed during conception, development, as well as in service. To address those challenges, some of the most critical engineering trends are: increased complexity is not only a market challenge, it is followed by an increased complexity that addresses the challenges on all levels of products, systems, and services, and this throughout the life cycle. Demand for more flexibility and choices. Customization is common practice today already and will even more so increase in the future. Improved product quality and robustness guarantee needs to happen upfront before a product or service is being launched. Digital transformation. To achieve all what I mentioned above, the various industries with their associated processes and beyond need to be more virtual than ever. This has to go well beyond traditional simulation department. It extends well into all aspects of an enterprise as well as our normal daily life. Sustainable innovation. From a business perspective, and a culture and processes need to be established that enable an innovation environment that guarantees sustainability for the business on the long run, despite the ever-changing boundary condition a business is operating in. The traditional basic principles are still holding true. To continue on the thought of sustainable innovation, here are some of the major trends that need to be considered to achieve sustainable innovation. Systems modeling and simulation is an essential piece for digital transformation for engineering-driven companies. The definition for SMS is provided here on the right. IIoT and Industry 4.0. The operational element takes more of a center stage within digital transformation initiatives and its linkage to the overall virtual engineering effort. We are in an era of new manufacturing already. Big data and IoT. Not only manufacturing, but even more so in our current time we live in, from an experience-driven environment perspective. We have, in order to account for that, lots of information needs to be collected and analyzed. This is resulting in the way we collect and distribute data that is changing rapidly. And of course, we need to make sure that the infrastructure is enabled appropriately. Iterative and collaborative approaches. What was mentioned before requires new iterative and collaborative approaches. They are closed-loop approaches and span not just across domain within enterprise, but also across organization and the entire supply chain ecosystem. Cognitive engineering is the highest maturity level. This is where we start really to talk about advanced optimization and advanced analytics capabilities, where predictive analytics is part of it. There are, of course, other elements and capabilities associated with this maturity, such as deep learning and the digital twin. Here is really where we start to talk about the digital twin capability. During this talk, we will further focus on the various elements that are the most important to help to get to this level in terms of the digital twin. As indicated earlier, we rely for most of our activities on data, but not only do we want to have access to the data, but also want to make use of it, connected so it can become information. It is a competitive advantage how fast companies access and make use of the data. At the top level, we are talking about innovating at the speed of thought. We will get back to this later during the presentations. With customers demanding better connectivity, efficiency, and safety in automobiles, electronic content in terms of value is surging. By 2030, the overall cost of electronics in cars is expected to rise to 50% of the total car cost. This will hugely increase the complexity of the vehicle system, which can't be managed efficiently using traditional approaches. Furthermore, new opportunities for services like smart parking management, paper insurance, leasing models, location-based ads, and more are expected to generate over $1.3 trillion for OEMs by 2030. This is all part of a future experience-driven consumer environment. Those are some elements driving the future automotive ecosystem that will see quite a few new participants. To make this work, they all need to embrace collaboration for seamless exchange of data to create win-win opportunities for all, as well as new approaches that make use and react to the data and information as it comes in and not just after the fact. Here are some challenges for automotive organizations across the value functions where the digital twin can play a central role in overcoming these challenges. Stakeholders across the organization lack holistic view of as data is created and managed in silos. This leads to suboptimal decision or trade-offs in engineering, manufacturing, and after-sales and service functions. With mass customizations, organizations are forced to cater to their customers' unique needs, leading to proliferation of product, features, and options. Automotive product recalls and warranty costs result in multi-billion-dollar spending due to poor quality of products designed, produced, and serviced. Interaction of product and manufacturing processes with the environment is complex and requires advanced simulation and what-if scenarios analysis, which typically does not exist today. The existing knowledge of hands-on system thinking leaves the organization with the baby boomers. Generation Y or Z employees have different aspirations, which can impact the retention of system knowledge relative to understanding the product fit, form, and function behavior across its life cycle. With the stage set, let's dive into the details of the digital twin and AI. When looking at the Gartner hype cycle for emerging technologies from 2018, it is interesting to see that the digital twin is currently only at the peak of inflated expectations. This is when looking at the digital twin overall. When going into more details, one can see that there are pockets in the various industries that are further ahead, but this would be part of another discussion. Here we want to highlight a few technologies that are closely linked with the digital twin capability. IoT platforms, 5G, autonomous driving capabilities of varying levels, various levels of artificial intelligence, and of course, data security needs to have a central role when talking about sharing of information and collaboration throughout the supply chain and across ecosystems. Before going further into the discussion and in order to speak the same language, let's define what a digital twin and artificial intelligence are. A digital twin refers to a digital surrogate that is a description of a physical asset, such as one or more products, processes, systems, people, and devices that can be used for various purposes. It makes use of data to and from its real-world asset and may change in tandem throughout the life cycle of the physical asset. Data going to and from the digital twin is like the blood needed to be alive. A proper architecture is needed to enable that data flow. This is shown with this high-level architectural view. In addition, it shows additional main elements that need to be enabled for proper functioning of the digital twin, like the data backbone with the business environment, innovation environment, various operational systems that generate and manage data processes at various lifecycle stages, and of course, the analytics engine that makes sense of the data, turning it into information and insight supporting decision-making. This brings us to the characteristics of a digital twin. And I mentioned this already. We need to make sure we are connected to a real world physical assets. We are using data, we are collecting and providing data back from the model. And of course, in order to generate business value, we make use of AI, machine learning, deep learning, and optimization techniques. This brings us to what is artificial intelligence. The term artificial intelligence is often used to describe machines or computers that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. And again, I would like to highlight here, cognitive, we are learning from data, we are able to predict something, what is happening in the future, and we are supporting decision-making. Machine learning and deep learning are a subset, and their usage defines the digital twin capability. You will see this later throughout the presentation. In automotive context, an example could be, for instance, preventive maintenance to avoid vehicle breakdown. On the deep learning side, quality inspection of components on the manufacturing shop floor using training images. And this is when we are talking about visualization, augmented reality. To position the digital twin, the traditional understanding of the life cycle of a product or process needs to change from a sequential to an iterative view at every stage based on a closed-loop process. At the same time, the traditional understanding of the system engineering needs to be expanded. This slide is used to explain the model-based system engineering process, MBSE, and expansion towards a digital twin in a simpler way. We defined SMS earlier and identified MBSE as a subset. Furthermore, it becomes clear that IIoT Industry 4.0 and IoT are changing the way we need to think about the traditional sequential and stage-gate product development lifecycle approach. Subsequently, the digital twin is going beyond the traditional thinking and scope of system engineering B. Systems modeling and simulation is the promotion of the effective utilization and advancement of requirements, guided modeling and simulation technology. Might it be from the lower to the higher fidelity, 0D to 4D, functional logic and physical models over time. And this is what we commonly call the digital thread. This is in order to predict and optimize behavior and performance, starting from detailed designs to complex cyber-physical systems throughout the digital enterprise. Supply chain operating environment. It applies to all stages of the lifecycle, starting from early ideation through development, manufacturing, operation, and retirement, and is iterative by nature. Based on the specifics of the role and purpose within the ecosystem, the digital twin can be created for a variety of different purposes and domains. Per definition, as I provided earlier, elements for those domains can come from products, processes, people, places, systems, and devices. They find their way into various application segments. We call those segments the application streams of the digital twin within the ecosystem. The complexity seems almost endless. The focus of these figures is on the engineering industrial side of the digital twin, here with product and processes. Since human behavior and society can and needs to be modeled and predicted as well, we mentioned this possible portion of a digital twin for completeness. For simplicity, it is captured for this purpose of this presentation under society. Future presentation and publication will have more discussion on this particular application stream. The benefits of the digital twin to organizations are quite a few. Here we want to mention just a few across the ecosystem. And I would like you to look at the center. Again, we are following the idea of people, organization, processes, products, and then the customer. That thinking needs to be in the center of it. And then, of course, when we are talking about the ecosystem itself, might it be product design, development, through manufacturing, sales and marketing, up to connectivity and value-added services in the field. And this is when we look, again, also in association, reduce time to market, improve the productivity, first time right, improve customer satisfaction by predicting failures proactively before they happen to avoid them. You can read this on the slide yourself. But there's a huge variety, as I mentioned before, for the benefits of a digital twin for an organization. Since we just learned that the main differentiation is in the process category, let's focus on the main elements in this category defining the digital twin maturity. There are quite a few process elements that need to be considered, and they're popping up here automatically on the screen. So please have a look. Each of those elements have their own maturity level. They are all interconnected. The maturity of each of the elements contributes to the overall digital twin maturity. To go into the details of each of those elements would go way beyond the limits of this talk today. And I just talked about the key elements for the digital twin for the process category. In this slide, I've shown the general steps for an engineering-driven organization of how to move towards higher levels of maturity. Traditionally, companies use test-driven development approaches. This is followed by the document-based approach. The vast majority of organizations have at least this level of maturity already established. Without this, they wouldn't be able to stay in business at all. The question, though, is how good is their implementation? Still, especially in our day and age, simulation is key or needs to be key to enable and to develop new products and services in order to stay competitive. Model-based development and support is essential. Most of the time, these are independent models still. Teams are operating way too often still in silos. To move towards MBSE, models need to be integrated. The top level is represented by cognitive principles. This is the level of systems modeling and simulation and associated with innovating at the speed of thought, what I mentioned earlier. All those stages need to be enabled in the journey of the digital transformation for engineering-driven organization. This is how the engineering maturity in all its facets can be increased. So far, I didn't mention the content underneath the text boxes. They represent the focus on process-driven foundational element. Here we can find again some of the key elements that need to be enabled to reach a specific capability and thus systems modeling and simulation maturity of an engineering organization. This includes also the digital twin capability. I just talked about the key elements for the digital twin for the process category. They are all linked one way or the other to the system engineering principles when I talked about the system engineering B. All this needs to be balanced following the main three maturity category: organization, process, technology. In addition, we have shown when moving up, we can increase the maturity of an organization. I would like to highlight once more that I always talked about the maturity of the digital twin in connection with process-driven elements. This was done on purpose. The digital twin itself is a capability and not a technology. There are enabling elements mentioned earlier that don't just represent process element, but also technology element. This underscores that a digital twin is being enabled by the means of lots of different technologies and enabling processes. With that being said, let's have a look at what point we can talk about the digital twin when discussing business maturity, again in high-level terms. Before going further on this slide, I'd like to focus your attention on the size of the portions for vehicle lab, bench lab, and virtual lab, and how they are changing when moving from the left to the right. I've shown already the levels reactive, which are associated with laggards on the market. Adaptive, associated with traditional run businesses, and proactive. They are linked to modern businesses that are leaders in their segments. I mentioned the top level is cognitive. Also on the business side, we assign this term cognitive to the business level maturity. As previously mentioned, this level is associated with implemented systems modeling and simulation capabilities. There might be some companies out there that have in some areas of the organization SMS principles enabled, but we don't see organizations yet that have it as a whole successfully done. Coming back to the digital twin, you can see that we have it starting only at a point where significant virtual lab capabilities are enabled in an organization. Without those, it wouldn't make sense even to discuss a digital twin maturity. The high-level architecture for the digital twin, as we talked about this earlier, provides some indication of the complexity of the ecosystem infrastructure needed to enable the digital twin. Let's have a look what sequence of enablement we need to keep in mind, as well as infrastructure elements we need to consider when deploying digital twin capabilities. To make use of the digital twin requires enabling the flow of information, data, from the real-world physical asset to the virtual model, and of course back. For the manufacturing operation environment, this would be IIoT, while for the service environment, typically this would be IoT. Enablement of IIoT and IoT capabilities is an essential prerequisite for the digital twin. Only at that point, one can take advantage of deep learning algorithm. Traditional deep learning is associated with machine learning. For the overall understanding of digital twin enablement, this thinking needs to be broader. It needs to extend to the service field as well. The final level will enable predictive prescriptive analytics. All those steps need to take place, and the proper infrastructure has to be established for the analytics engine to function smoothly. Enabling those levels are prerequisite for cognitive engineering capability. When discussing the real-time digital twin capability, especially on a cognitive level, there needs to be a discussion about the surrounding infrastructure. Especially, there is currently a lot of discussion regarding connectivity between devices, databases, and compute systems. The emerging high-speed 5G network infrastructure will be a major enabler for higher-level digital twin maturity. Countries investing into this infrastructure will very likely have the first mover advantage. Furthermore, closed-loop systems need to be enabled. Edge computing becomes standard practice in addition to high-performance computing and cloud compute capabilities. In addition, an absolute essential element of the infrastructure is scalability. How often did we have to realize that when systems went down when deployed and being hit all of a sudden with real-world use load? These mentioned elements are in their way also contributing to enabling, innovating at the speed of thought. Since I mentioned several times already how essential IoT is, let me make some brief comments about the general steps needed to get this transformation off the ground. You can see on this slide that the digital twin is mentioned at the level of initial digitalization efforts for the first time when looking at the operation side of the business. And since I mentioned network infrastructure on the previous slide, let's highlight that connectivity is one of the first steps that needs to be taken care of. This brings me back to my earlier comments. It is very important to understand that each of the enabling maturity elements have their own maturity level consideration and that they are linked with each other. Let's talk briefly about innovation maturity. The bottom level is product improvement. Today, companies understand that they must go beyond the typical S-curve to stay competitive. This moves companies to the higher level of product redesign. It was mentioned earlier, this is where most companies operate today. It also can be described with incremental changes in behavior. To go beyond this level, companies need to start the journey of digital transformation. During the first stages of that transformation, companies can achieve functional innovation. When a company organization enables cognitive digital twin capability, it grants a business the coveted ability to reach a new horizon of system innovation and an enviable position to disrupt the market, to be a leader on the market. Systems innovation is defined by the way a company uses the information that is available. And this brings us back to innovating at the speed of thought. Predictive and analytic capabilities overall play a vital role in enabling the movement towards this top level of maturity. This gives us clear indication where the digital twin needs to be placed. The digital twin capabilities, as I mentioned, plays a key role in achieving higher levels of innovation maturity for a company and the engineering environment. In the end, what it comes down to is innovate or die. Even though the digital twin is, as an idea and practice, has been around for a while, there is still quite a bit of hype associated with it. Just because people are talking about the digital twin doesn't mean they have the proper understanding of what is involved to properly and fully implement such a concept. In addition, there isn't just one spot we can put a digital twin on the hype curve. As we outlined before, we must differentiate the maturity for the various application streams, which will vary by industry and even by company within various industry segments. Might it be automotive, aerospace, high tech, etc. The majority of the industry is still at the first upslope. Even lots of those with product-focused digital twins in the field utilizing initial principles of IoT functionality. Only a few early adoption leaders have gone beyond the peak of inflated expectations. They are typically focused on the machinery and equipment industries utilizing IoT functionalities, as well as certain aspects of social media utilizing artificial intelligence capabilities. Those companies realize the complexity of the required architecture much better than all the other companies. Good examples of these early adopters are companies leading in development of autonomous or semi-autonomous driving technology, as well as electrical vehicle systems. Still, to make the turning point through a trough of disillusionment, another important understanding needs to take hold. Areas where we see elements around this turning point are the thought leaders utilizing IoT and focusing on Industry 4.0, as well as application of social media using latest AI capabilities. Here on this slide, I would like to mention a few essential steps in order to deploy system modeling and simulation in order to achieve the capabilities needed for digital twin. Fundamental understanding is needed for planning, governing, education, execution. What team and council needs to be in place? What is the core team? And in order to execute properly, we need to understand where we are in order to move forward, in order to identify where we want to be and what gaps are associated with it. This will help us to develop solutions and the roadmap in order to achieve what we are looking for with the to-be status. But this is not enough. We need to change the way we execute, and this needs to be an end-to-end approach. This is consulting, execute, deploy, and guide the solution, educate and train, use proper pilot projects, involve the vendor, engage the vendor with the end consumer together, form a partnership with the customer. This is what we are talking about when having an end-to-end execution approach available. Before going into the case study, I wanted to show you here some of the offerings that we can provide here. And this is representing an end-to-end approach, as I mentioned before, and considering the know-how what is there from a holistic point of view, going into deep of the trenches and help companies to make the transition and to enable digital twin capabilities on all the levels. With that, I would like to turn over to BJ.
Thanks, Frank. Frank covered the digital twin conceptual frameworks, and I'm here to share with you how these concepts can be applied for your respective business challenges to unlock business value. The use cases of digital twins span across product development, supply chain, manufacturing, and after-sales and service domains. We have addressed all these use cases comprehensively in our white paper, which will be shared with you post this webinar. In the interest of time, I will pick up one use case from engineering and service domain to demonstrate how a digital twin can be modeled using artificial intelligence. The use case that I will debrief you is predictive reliability. Unpredictable reliability destroys wealth across the mobility ecosystem. It impacts your company, your customers, your community, and the entire carbon footprint. In the context of company, quality manager encounters high defects per vehicle. Engineering manager faces higher lead time to identify root causes of failures. It is just not the OEM alone. Even vehicle owners or fleet owners have to experience high vehicle downtime. The impact is economically significant as well. In 2019, the global automotive industry had spent about $49 billion in warranty cost. 53 million vehicles have been recalled in US alone, and 3.6 million times cars have experienced breakdowns. Conventionally, OEMs use statistical tools and techniques to predict failures using historical data. They are inefficient, inaccurate, and mostly reactive in nature. Hence, predictive reliability of assets or vehicles is the need of the hour. Every asset can be potentially connected to internet to exchange data. Imagine this, with hundreds of ECUs, every car potentially transmits 25 GB of telematics data per hour. And this data is the newest form of raw material to build better, reliable products. The capabilities that are required to model digital twin are listed here. At the heart of the digital twins lie virtual model. These models can be either multiphysics model based or data driven models, or it can be even a combination of both. The choice of such virtual models depend on the problem that needs to be solved. What is more important is the capability to achieve recommendations for actions, as Frank highlighted earlier. AI models should not be a mere black box. Rather, they must be much more explainable. We call this as explainable AI. Simply put, explainable AI is a set of machine learning algorithms that generate outcomes that can be understood by human beings and can be tracked backwards to the origin of the business problem. In order to achieve explainable AI, data engineering is foundational. In this example, we will cover a data-driven model with a complex asset like IC engines. With this example, the framework can be extended to any of the discrete manufacturing products in the context of reliability. Now, what you see here is an example of a diesel engine, and we will take diesel engine as an example to show AI model development. The specifications of the engine are highlighted here. I will not dwell into details, but let's take a step back to understand the possible business drivers. Let's say your organization may launch a product in a new market and will be keen to avoid the failures of products in this new launch that were encountered earlier. Or let's say if your business is asset intensive and become livelihoods for people or other businesses like trucks or construction equipments, you may want to proactively plan for spare parts or even service technicians to avoid asset downtime. These drivers demand better understanding of your product usage conditions to avoid failures of your new product launch. Alternatively, you should also want to come out with new business models like pay-per-use. We will cover how service managers predicted immediate failures and engineering managers understood the behavior of their products with this example. The engine that we have used here is for automotive application, and we have used both telematics and service repairs data for the AI model. The high-level approach is shown here. Again, without deep diving into details, let's get into a very high-level macro picture of how did we solve this problem. Once we identified a business problem to be solved, we assessed the data sets for maturity. Fusing different types of data is a critical requirement of a digital twin because different data sets have different attributes and can unlock exponential business value. With our experiences, we found that while model building and validation takes 25% of time, pre-processing of data and extracting relevant features take 75% of the time in a typical data-driven model development like this. Now, we tapped in the telematics system, dealer management system to acquire the data. And Frank mentioned that IIoT is an important foundation for even having a digital twin in place. Now, post the data have been acquired, we have used multiple data sets that have been shown here. And these data sets help us to feed the machine learning workbench. We have built a machine learning workbench which consists of algorithms specific to automotive domain to provide contextual intelligence for self-learning. Machine learning model was trained and validated to identify correlations with respect to different parameters and the failure lead indicators to classify them as failures. What you see here on their screen is an example of how we have modeled the digital twin using AI. Digital twin is very contextual and specific. Engineering manager here can understand the behavior of an engine by changing the key parameters like speed and torque. With this time-bounded analysis, he is able to understand the product behavior and establish traceability of the boundary conditions in the field. And you can see how he can easily see the health score of the asset much more intuitively. Engineered with a closed-loop feedback system, a good characteristic of digital twin is to help every stakeholder in the organization to receive personalized failure insights or recommendations. Now, as you can see here, in point number 4, service manager already received 2 recommendations that the exhaust system is about to fail in the next 497 miles, and a wrong part was replaced in the service center. Engineering manager gets a recommendation in terms of correlation of parameters for his root cause analysis. We observed that the combination of parameters like engine coolant temperature rise, state dwell, engine power, or some of the lead indicators of exhaust gas recirculation cooler failure. While with these recommendations, service manager can take proactive actions for planning spare parts, or engineering managers to use these insights to improve product reliability. Now, validating the model is an important step to realize the business value. We have validated the model with metrics like precision, recall, and precision recall curve, and made sure that the AI model predicts failures proactively without missing any of them. Then this model was exported and converted into production grade. Based on our experiences, usage of domain expertise to pick and derive the features, handling the data quality issues using app data engineering strategies, and focusing on the right machine learning model performance metrics are the critical success factors of machine learning or AI phase in a data-driven modeling approach. With such data-driven digital twins, we have helped the engineering teams to reduce the lead time of root cause analysis from months to days. We have reduced vehicle downtime for service managers, and eventually it helped them to reduce up to 30% of warranty cost as well. Just to summarize what we have seen how data-driven models using artificial intelligence can create purposeful digital transformation to solve specific business problems in the context of reliability, benefiting engineering managers, service managers, and quality managers. Artificial intelligence has immense potential to avoid recalls or even deliver better mobility experiences or create new business models for our ecosystem. While the use case shared here is only for engineering and service domains and specifically articulated for engine, digital twins can be extended for manufacturing domain as well, reusing most of the components of the framework demonstrated here. Similarly, digital twins can be extended for electric powertrains or electric vehicles to optimize the battery performance and thermal management as well. With this case study, I would now hand over it to Ed to summarize the key takeaways for you. Over to you, Ed.
Thank you, Vijay. To wrap our presentation up, let's look at the critical success factors for the digital transformation. Customers realize that an investment must be made in organization, process, and technology. We've already covered this a couple of times. In order to drive an innovative culture or innovation culture, organizational components must be transformed to increase communication and collaboration against those typically disparate silos. Education is a cornerstone of this organizational transformation, and this is to ensure that the rollout is easily understood by all levels of management, including executives. The message here is keep it simple. The next transformation must be in process. By adopting agile and adaptive methodologies and effective governance, a solid data foundation and backbone can be achieved, resulting in effective simulation-driven engineering. The third transformation will be technology. Artificial intelligence coupled with augmented and virtual reality will help the cognitive abilities needed for future product development. IoT and IIoT need to be enabled as well. The business benefits will be reduced time to market, reduced physical prototypes, reduced reworks, increased reliability, lower warranty costs, and new revenue streams will be created. There's many more factors involved in a successful digital transformation. This overview is only intended to show some of the most critical ones. Okay, in summary, the digital twin offers an enterprise improved product quality. You can look into predicting field failures, improve the product life, and in the end, improve your customer relationships. So there's so much more. The successful journey toward maturing through the various stages of the digital twin are once again the realization that changes in organization, process, and technology need to take place. Commitments from all levels of management, practitioners, and insightful field data, trusted data, and I want to emphasize trusted, will significantly improve the overall development, manufacturing, and field support experiences. Collaboration among these groups is the lifeblood of the implementation. The successful adoption and transitional maturity of the digital twin, it will take dedication, it's going to take time, and it's going to take patience. Now let's take a look at what the definition is again. A digital twin refers to this digital surrogate of a real physical asset. I'm not going to read the entire definition, it was already covered. But we are not just making this up. This is as a result of a lot of extensive work from the INCOSI NAFEM's System Modeling and Simulation Working Group Terms and Definitions Committee. So this is recognized by many global not-for-profit organizations. So what is a digital twin and what isn't a digital twin? A digital twin is a surrogate of physical assets. Could be products, processes, systems, and people. It's not an aggregate or extension of 3D models, simulation models, physical tests, and sensor data. What it is, it's a framework and is technology driven. It's capability. It's not a technology. It's not a product that you install. The digital twin has business value driven with specific use cases. It is not one size fits all. It's like a fingerprint. Each one will be different. IoT, AI, and machine learning enable a digital twin. It's not synonymous to IoT, AI, and ML. Multiple levels of maturity defined by the life cycle stages and enabling technologies is a characteristic of a digital twin. Single maturity level is not. It's a living, breathing entity. Dynamic updates and data in the life cycle. These updates happen all the time. It's not static and created only once in the life cycle. That is a model. That's not a digital twin. The implementation of the digital twin is a journey, yes. And it's, as I mentioned, it's not a software product or platform or an implementation. It's a living, breathing creature. Okay. Now, what I'd like to do is I'd like to thank you for your attention. This has been a wonderful experience for all of us. The fusion of Hinduja Tech and the SMS think tank is what I feel the next stage of evolution in providing end-to-end global engineering consulting and services to the automotive industry and guiding a company on its digital transformation journey. There will be more interactive sessions as well as publications on this topic of the digital twin, as well as other areas, including model-based systems engineering, model-based design, and others. I'm going to, after I mention a post-webinar kit, for those participants or those people that would like, we are offering a fulfillment package which has a complimentary white paper that Hinduja Tech and the SMS think tank co-authored. You'll have a link to the recorded session, the answers to key questions, and feedback on the webinar. So please send your contact details from your work email ID to marketing@hindujatech.com. At this time, I would like to open the floor to questions.
Thank you, Ed. I think we have got already quite a amount of questions. So I'm going to broadcast that into the screen right now. The first question is from Karthik. So let me just open it up on the screen.
Let me answer this one if I may. There is, yes, we talk about physical assets. What's important is that there's a lot of confusion globally on what a digital twin is. People think that if you have a virtual model and you create a 3D part, that virtual model becomes the digital twin. That is not correct. That virtual model is a model. That's all it is a model. There is no linkage between the physical asset, maybe sensor data coming in from the physical asset, or any way to predict the maintenance or what's really happening out in the real world. So you need the characteristics, the operating environment. You need sensor data, a lot of this data to feed into the virtual model to make the prescriptions to say, we're going to have a failure at this point if we don't do something quickly. We need maintenance. Oh, look, we keep on having reoccurring problems in this area. Let's talk to the design folks. So it's a marriage between the virtual space and the real world space. It must be closed loop and it must be consistent and must have trusted data. Hopefully that answered your question.
Gary, so that's on the screen now.
A few examples would be, take for instance, the manufacturing area. It could be the whole manufacturing line that you have modeled in order to help the logistics to optimize the whole process throughout the line. But at the same time, in order to support this efficiency for the whole line, you need to be able to have models replicating each machine equipment in the line. So you create digital twins for each of the equipments. That would be one of those examples. Another one, and again, we have to think from outside of the box. Take, for instance, fleet management, autonomous driving fleet capabilities. You can take the whole fleet, but at the same time, you can also take what is directly on a specific vehicle in order to react properly to the environment outside. So you have a larger model with a fleet, you have a specific digital twin for a specific car in there as well. And this is not just in order to improve performance and behavior, but also, as Vijay mentioned before, predictive maintenance. So nothing is breaking down, but actually you bring it back and repair it. So you have you reduce your costs significantly. So this would be some of the ideas. So big system, smaller system, it depends on the perspective you're looking at.
Thank you, Frank. The next question is from Jabastin Charles.
I can take this, and Frank, you can add in, Vijay, you can add in. But when we refer to cognitive, we've mentioned that a number of times. Cognitive means a way of thinking, like a human mind thinks. So we would have those predictive analytics, that artificial intelligence built in to this application of a digital twin, so it can mimic real world human thought. So cognitive is that advanced stage where you have built in such an automation of thinking that that whether it be failed failures, whether it be maintenance, the machine can actually make decisions. So cognitive is the highest level of the mimicking human thought. Your words on that, Frank?
Yeah, I think that explains it pretty good.
Okay.
All right, so there is one more question. I think this will be the last question because we are very close to the time.
How close are we? I think The uncertainty itself, when you're looking into the model itself, on the simulation side, we do uncertainty quantification and qualification for quite a while already. The question is how we bring it into the real life, into the digital twin. Again, this is where we need to talk about the connectivity. How fast are our models or a specific digital twin, which is close to the asset or directly located on the asset? So we have to talk about how we can bring down the size of the model in order to have a real-time or close to real-time interaction. So uncertainty quantification exists already today offline, which is for a while already part of simulation techniques. But really, to bring it's where we are talking about connectivity, etc. This is where I talked about 5G quite a bit.
Thanks, Frank. So one more question from Balaji. So I think it goes to Vijay Balu.
So what mission algorithm was used in the case study for the failure prediction? So we have used neural networks, and autoencoder is one of the type of neural networks that we have used in the case study for the failure prediction.
Thank you, Vijay. If you allow me, I can show one more question from Rajkumar.
The answer in general is yes. Yeah, and this is I'm referring back, and I have to go back to, is the proper infrastructure in place in order to make use of the data? And of course, when we are talking real-time collecting data, we have to understand what data really we need to collect, not just collect masses of data, but collect the data which is really needed. Otherwise, we overwhelm the whole system. So you can overdo it. So before you really release your digital twin into operation, communicating with the real world asset, you make sure that you have a strategy, a data collection strategy, and analysis strategy set in order to provide that information back. And in between, this is part of how much storage you have on the vehicle and off the vehicle, what is close to real time, what needs to be brought back in order to update the algorithm if needed.
I want to add that there's lots of questions here, and I'm delighted that we're getting these. And we will be responding to all questions that we did not have time to answer. So if you've submitted a question, we will respond to you.
I just wanted to add what Frank said in the previous question on a digital twin of a product. So in our white paper, we have articulated the data potential from cradle to grave of a product. There is testing data, there is simulation data, there is real-time streaming telematics data. So probably after the webinar, the white paper will help you to understand the potential of data and how that data can be used in terms of modeling a digital twin, right from design to scrap.
All right. Thank you very much for your time, all the speakers and all the participants in LinkedIn. Thank you very much. Please drop in your email address to marketing@hindujatech.com. You will receive a complimentary white paper. Thank you very much. Appreciate your time. Thank you.
Yeah.